Okay, guys, welcome to Physics 390 class 15. This class will be on bosons and fermions. Bosons and fermions are two classes of particles. Bosons are the force-carrying particles like the pion and the photon. Fermions are the matter particles like the electron, proton, neutron, and others. And we'll be looking at two particle wave functions and how they differ between bosons and fermions, and something called symmetric and antisymmetric wave functions. And this comes from chapter 5.1 of our textbook. Okay, so an introduction to two particle systems. So we've done some one particle systems. Now let's look at two particles. So a two particle system has a wave function, which is a function of two position variables, R1 and R2. Since there's two particles, each R1 would refer to the position of particle 1, R2, the position of particle 2. So it's a function of two position variables in time. It satisfies IH bar d psi dt equals h psi, which is the time-dependent Schrodinger equation, where H is the Hamiltonian operator, will be the kinetic energy operator for particle 1, and the kinetic energy operator for particle 2, and then the potential for particles 1 and 2. So this is a generalization of the single particle system, where we only have one term for the kinetic energy, and the potential is only a function of one position variable. So the time-independent Schrodinger equation, or TISC, becomes similar here. The kinetic energy term for first particle, the kinetic energy term for the second particle, plus the potential is equal to E times psi, where psi is a function of R1 and R2, but not time here since it's time-independent. So how can we solve this? It's got lots of variables in it. It was already challenging to solve the one particle Schrodinger equation. How can we solve two? Well, in general, it's pretty tough, but there are a couple situations where we can make progress. If we have non-interacting particles, particles 1 and 2 don't directly interact with each other, so that their potential V(R1) and R2 is just separately potential of V1 of R1 plus V2 of R2. So they're separately interacting with the surroundings, but not with each other, because R1 and R2 are not together in a potential. Then the TISC actually separates into two one-particle equations. So this is shown in the textbook. I won't show all the steps here, but it separates into two one-particle equations. And the combined wave function separates into two parts. A wave function psi A for the first particle and a wave function psi B for the second particle, which are just separated and multiplied by each other to give the total wave function. And then the energy is just the separate energy of particle A and particle B added together. There's no interaction energy between them. So that's a situation we can handle, non-interacting particles. Another situation we can handle is particles interacting via a central potential. And a great example of this is the hydrogen atom, which we've already looked at, which has the proton and the electron attracting via the electrical central potential. There we ignored the proton, or we just took it as fixed at the center. But it's actually possible to do it as a two-particle system with the proton just moving a lot less than the electron. And so in that case, we have V of R1 and R2, where R1 might be the proton and R2 the electron, is a function of just the distance between R1 and R2. So, or the vector connecting R1 and R2. So the distance between the electron and the proton, say. And in this case, it's also possible to separate the TISC into two equations. The two equations turn out to be the center of mass, which is the center of mass of the hydrogen atom, which turns out to work as a free particle. So the hydrogen atom can move about freely. And then the other equation has to do with the relative position of the electron and the proton. And that's the one that has the energy levels and the bound states that we saw when we did the hydrogen atom. Okay, so there's a couple cases where two particle systems can be handled, non-interacting particles and particles interacting via central potential. In general, though, solving two particle systems or even more particles for, like, say, a carbon atom has a nucleus and 6 electrons, so that would be 7 total particles, is quite hard. So, for example, if we look at the helium atom, which has a nucleus and 2 electrons, the potential for R1 and R2 would be K, or 1 over 4 pi epsilon naught, times the attraction between the positive nucleus and the first electron, which would be given by this potential, then the attraction between the second electron, R2, and the nucleus, which would be this potential, and then the mutual repulsion between the 2 electrons themselves. So you can see that this is kind of a mixture of non-interacting particles. If just these first 2 terms are here, this would be non-interacting. And if just this third term were here, it would be a central potential. But we have a mixture of these 2. And so we can't separate into 2 one-particle equations here. And so solving this is hard. And we'll look at the helium atom later this semester. So, okay. So let's get on to what we were talking about, bosons and fermions and their wave functions. So the 2-particle wave function, which we were just talking about, psi R1, R2, is psi, a wave function A for the first particle and a wave function B for the second particle. That assumes we can tell particles 1 and 2 apart, because we have to know that particle 1 is in wave function A and particle 2 is in wave function B. But why couldn't particle 1 be in wave function B and particle 2 be in wave function A? So we have to be able to tell them apart, the particles apart, to be able to write this wave function like this. It turns out in quantum mechanics, for identical particles like electrons, we can't actually tell the particles apart. One electron looks like every other electron. It's just simply not possible to label electrons 1 and 2 in a meaningful way. So for that reason, we have to write a different form for this 2-particle wave function. We write psi either plus or minus R1 and R2 is some normalization constant A of psi A R1 psi B R2 plus or minus psi B R1 psi A R2. So what we've done here is the first term we have A paired with 1 and B paired with 2. The second term we have B paired with 1 and A paired with 2. Okay, and there's 2 ways to do this. The plus sign is called symmetric. So there it's symmetric. We add psi A R1 psi B R2 to psi B R1 psi A R2. The minus sign is called antisymmetric, where we subtract off psi B R1 psi A R2 from psi A R1 psi B R2. The upper sign, or plus sign, applies to bosons. Okay, so bosons are a type of particle, as we already mentioned in the very beginning of this video, or a class of particle. And these are symmetric under interchange of 2 particles. So if you look at this for the plus sign, if we switch R1 and R2, since there's a plus sign here, we get the same thing. We switch R1 and R2, these two terms just switch, and we get the same thing back again. So we get psi plus of R2 R1 is psi plus of R1 R2. So that means it's symmetric under interchange of the 2 particles. The wave function is exactly the same if we switch the 2 particles. The minus sign, the lower sign, is for fermions. These are antisymmetric under interchange of the 2 particles. So if we take psi minus of R2 and R1, we get minus psi minus of R1 and R2. That's because if we switch R1 and R2 here, we actually get, because of this minus sign, if we switch R1 and R2, we actually get the negative of what we would get with R2 and R1, which you can verify if you just write this out and switch R1 and R2 and compare the two, what you get for R2 and R1 to R1 and R2. Okay. So we have, and this is the defining property actually of bosons and fermions, that under interchange of the coordinates of the two particles, bosons, the wave function keeps the same sign. For fermions, under interchange of two identical fermions in a wave function, the wave function switches signs. Now it turns out, I should say, note in both cases, the reason we can do this, and it makes physical sense, is that the square of the wave function is unchanged by the exchange. If we exchange R2 and R1 here, we get the same wave function back again. So clearly psi plus squared doesn't change, which is the probability of the probability coming out of the wave function. But even if we take the negative of psi minus, that is, if switching the two coordinates switches the sign of the wave function, when we take the modulus squared, the minus sign goes away, and we get the wave function squared is not changed by exchanging R1 and R2 for fermions or bosons. So these are the two alternatives we have to keep the square of the wave function unchanged. Either the switching R2 and R1 doesn't change the sign of the wave function, or it makes it negative. In either case, the square stays the same. So that's why there are two classes of particles, bosons and fermions. Now, it can be shown that because as a consequence of this property, which defines bosons, that all bosons have integer spin. And this is called the spin statistics theorem. It's a fairly advanced theorem, but we'll just take it on faith, that all bosons have integer spin, pions, photons, etc., etc. Pions have spin 0, photons spin 1, gravitons spin 2, etc. Meanwhile, all fermions it can be shown from this property, have half integer spin. That would be electrons, protons, neutrons with spin a half, spin 3 halves. There's some particles with strange quarks which have spin 3 halves. Some atoms have spin 3 halves, spin 5 halves, etc. Okay, so one very interesting thing that comes out of this antisymmetric property of fermions is, note if we take the if this definition of fermions here, psi minus of R1 and R2, and we take psi A equal to psi B. So we try to put particles 1 and 2 into the same state, psi A, instead of different states, psi A and psi B. So we take A equal B, so we're putting them in the same state. What happens here? Well, if we have the minus sign, then we have psi A R1 minus psi A R2 minus psi A R1 psi A R2, which is 0. So we don't get any wave function at all. So that means, and therefore it can't be normalized. It doesn't give any probability density. So that's impossible. So that means that it's not possible, because of for fermions to be in the same state, to both share the same state. And that leads to something you might have heard of in chemistry or perhaps another physics course, is the Pauli exclusion principle, where two identical fermions cannot occupy the same state. Okay, so two electrons cannot occupy the same quantum state, since they're both fermions. And this has big implications for the behavior of both metals and of atoms, because in atoms we have electrons which are in successive states, and instead of all the electrons sharing, say, one state, the lowest energy state, the ground state of an atom, they have to occupy different states, which gives rise to the periodic table and the properties of atoms. So this is actually an extremely consequential physical principle, the Pauli exclusion principle. Okay, so let's move on. Let's look at socialization of particles. It turns out bosons turned out to be more social than fermions through something called exchange forces. So we can calculate the expectation value of the square of the separation distance for two particles in a two-particle wave function. So between the two particles in either psi plus for bosons or psi minus for fermions of this combined wave function. And what do we mean by the square of the separation distance? It would be the expectation value of x1 minus x2 squared for the x coordinate, say, just to keep things straightforward. We could do the same thing for the y coordinate or the z coordinate. So the expectation value of the square of the separation distance, which if we multiply it out using FOIL becomes x1 squared plus x2 squared expectation value minus 2 the expectation value of x1, x2. Okay, so we calculate this, and this is done, it's a little bit involved, but it's done for this combined wave function in the textbook for both the symmetric state, which is the boson state, and the antisymmetric state, with the minus, which is the fermion state. And this is what we get. So for we get the for plus and minus, we get the same three terms here. The expectation value of x squared in the state, quantum state A, plus the expectation value of this state B of x squared, minus 2 times the expectation value of x in the A state times the expectation value of x in the B state. But now here's where the difference shows up. Notice that for the plus sign for bosons, we have minus 2 times the square of this quantity xab, which is defined as the integral of x times the overlap of the two wave functions a and b. Okay, so this is just this definition here of xab. But notice that xab is squared, so this term is always, this term here that I'm circling is always positive. So if we have bosons, then our separation distance is going to be this collection here minus a positive number. Whereas if we have fermions, it's this same distance here plus a positive number. So we conclude that bosons have a smaller separations on average than fermions because we subtract off this distance for bosons, whereas we add it for fermions. So fermions tend to be further apart on average than bosons. So we can say, this is really interesting, there's an effective exchange force arising from the geometry of the wave function. When I say geometry, I mean whether it's symmetric or anti-symmetric under exchange of the particles, which causes fermions to effectively repel each other somewhat and bosons to attract each other somewhat. So that's why we say bosons are more social than fermions. Fermions tend to sort of repel and keep to themselves, occupy separate states. Bosons tend to attract each other and occupy common states. Note though that if in this expression, if psi A and psi B do not overlap, so if there's no overlap in position, no overlap of these two wave functions, then this xab term will be 0. So then this term drops out and there's no difference, there's no exchange force. And the two particles act as if they were distinguishable. There's no effect of them being bosons or fermions, even though fundamentally they are not distinguishable. So in quantum mechanics, all particles are either bosons or fermions. But if they're separated, if two electrons, let's say, are separated enough so that their overlap of their two wave functions is 0, we can act as if they were distinguishable. So luckily, this allows chemists to treat distant electrons as if they were distinguishable, say few. And this allows them to make a lot more progress in analyzing molecules. Molecules have lots of electrons, which in theory are all have to have a collective anti-symmetric wave function. But if they're distant, we can treat them as if they're distinguishable and kind of divide up the molecule into different parts and treat the different parts separately. So that's a good thing. Or it makes chemists able to do more and to make more analytical progress. Okay, to wrap up, let's add spin into the picture. We've recently talked about spin. How does that figure in? We haven't mentioned spin yet. Well, as we said, all elementary particles have spin. In fact, that's one of the properties of bosons and fermions, is that bosons have integer spin, fermions have half integer spin. So the full wave function would actually be a spatial part, psi of r, times a spin part, chi. Chi is the symbol that's most often used for the spin wave function. So for a single particle, it would be psi of r, just a single variable, position variable, times chi, a single particle's spin state. A two-particle state would be, again, what we said before, psi r1 and r2, and chi of 1 and 2. And the whole thing, the product of the spatial wave function and the spin wave function, must be symmetric under exchange of 1 and 2 for bosons, and anti-symmetric under exchange of 1 and 2 for fermions. So what does that mean? Well, for bosons, we can have if the whole thing must be symmetric under exchange of 1 and 2, we can either have the spatial part symmetric and the spin part symmetric, so that the whole thing is symmetric. Or we can have anti-symmetric space part, so when we switch, we get a -1, an anti-symmetric spin part, so when we switch that, we get a -1. And then the two -1s multiply to 1, and we have a symmetric total whole thing. So for bosons, we can have either symmetric space and symmetric spin states, or anti-symmetric space and anti-symmetric spin states, to have the whole thing be symmetric. For fermions, on the other hand, we need the whole thing to be anti-symmetric. So we can have symmetric space and anti-symmetric spin, because then when we switch the space, there's no sign change. When we switch the spin, there is a sign change. And so the whole thing changes sign, as it must for fermions. Or we can have anti-symmetric space and symmetric spin states. So when we switch the two position variables for the wave function, the spatial wave function, we get a -1. When we switch 1 and 2 for the spin state, we would get +1 since it's symmetric. Either way, we get a totally anti-symmetric state. The whole thing is anti-symmetric. So when we wrap spin in here, we get a little bit more complexity here and different possibilities for building up totally symmetric or totally anti-symmetric states. Okay, so let's just take an example here to connect this to something that you might be familiar with. So let's say we have two spin 1/2 particles, which are fermions. We actually have 4 ways to combine them into eigenstates of the combined spin of the two states. There's an anti-symmetric state, which is called the singlet state, which is normalized 1/√2 times up down for spin 1 and spin 2 minus down up for spin 1 and spin 2. So you can see if you exchange up 1 and 2, this would go to negative, because if we exchange 1 and 2 here, this would have the opposite sign as it has right here. So that's why it's anti-symmetric. On the other hand, there's 3 ways to combine two spin 1/2 particles that are symmetric. We can just have them both be spin up, because if we switch them, we still have both spin up. We can have normalized 1/√2 spin up, spin down plus spin down, spin up. If we switch those two, we get the same thing, so that's symmetric. Or we can have spin down, spin down. Okay, so that's the singlet and triplet states for two spin 1/2 particles. And just incidentally, the singlet state turns out to have total spin 0 when we combine these because the spins kind of cancel out. Whereas the symmetric or triplet has total spin 1 because we have two spin 1/2s pointing in the same direction. Okay, so what does this mean for two electrons? Well, two electrons with spins in the singlet state, which is asymmetric, must have a symmetric spatial state, okay? Because like we said, if the spin state is antisymmetric, then for fermions, the space state must be symmetric. So one possibility for a symmetric spin state is for psi A to be equal psi B in our symmetric spin state. And so if that's true, they would share the same spatial wave function, the two electrons. If their spins are in the singlet state, they can share the same spatial wave function because that's a symmetric possibility. And this is actually the origin of two electrons per orbital in chemistry. In chemistry, each orbital or each wave function admits two electrons, and that's because two electrons can share the same spatial wave function or orbital and be in the singlet state where there are two spins there in an antisymmetric spin state. Notice though, it's kind of interesting that they're not actually just spin up and spin down separately. It's a mixture of one being spin up and spin down and the other being spin down, and the first being spin down and the second being spin up. So it's not quite in the two electrons per orbital that one is spin up and one is spin down, although roughly speaking, that's okay to think that way. But in fact, this is the quantum state that the two electrons in a given spatial orbital would have in chemistry. Okay. So what have we looked at? Just a quick summary. We've looked at two particle wave functions, and we've seen that they're hard to solve, that there's a couple cases where we can solve them. Non-interacting particles, particles interacting through a central potential. But in general, like for the helium atom and bigger atoms, it's quite challenging to solve analytically. We've looked at the need to have symmetric and antisymmetric combinations of particles, symmetric giving boson particles, which have integer spin, antisymmetric giving fermions, which have half integer spin. And then the fact that bosons, as a result of this, have an effective attractive exchange force, so they spend time closer to each other than fermions. And then finally, when we include spin, we see that the total wave function, including space and spin, has to be symmetric for bosons and antisymmetric for fermions. And that gives several possibilities for how that can be achieved. And we see that we can get a little insight into the two electrons per orbital rule in chemistry. Okay, I hope you've enjoyed this video, and I will see you in class. Thanks.